We're all excited after lunch, had a good meal. So my name is Kate Hudson, and I work on the Firefox engineering team. And today I'm here to talk to you about building multi-process apps with React and Redux. So we do a lot of different things at Firefox, but what my team mostly focuses on is building user interfaces with web tech like React in such a way that they can still integrate with the rest of Firefox. So for some context, in most React apps, we only usually have one JavaScript runtime. So one event loop, one stack, one heap, et cetera, et cetera. But when you're running something like a user interface for Firefox, or a browser extension, or a desktop app in Electron, for example, you have to deal with different independently executing JavaScript runtimes that are communicating in some way. So that's what I mean by a multi-process app. Another kind of multi-process app is a single-page app that communicates with frames or workers, which Parashram is actually going to give a talk about tomorrow. So make sure you check that out. I'm definitely excited for it. So finally, you can also have an application in which your JavaScript processes, one or more of them, communicate with an entirely different platform or language, such as is the case with React Native on a mobile phone. So why do things this way? Well, multi-process apps allow us to reach a huge range of platforms beyond just the web. They give us more features. And finally, they give us new ways of optimizing our programs. And we get all of this while still getting to write JavaScript. And we love JavaScript, right? Yeah, JavaScript. The thing is, we pay a price for this. With more power comes more complexity. But thankfully at Firefox, we found that React and Redux have a lot of implicit patterns and constraints to help deal with this complexity. So React and Redux have a very useful model of the relationship between data and the view of data. State is also a major concern, and Redux gives us some excellent constraints to tell us what state should look like and how we should change it. They really prioritize testing. And finally, a lot of the parts of both React and Redux are composable, which is really important as your app expands in size and complexity. However, where React and Redux do not provide us with a lot of structure or constraints, and where we're not really often forced to think about explicitly in JavaScript, is this thing called concurrency. And managing concurrency is typically pretty difficult, and in my experience, it can also make the difference between making an application a complete success or a complete utter disaster. So, since I've only got like 25 minutes or whatever it is, what I'm really going to talk to you about is patterns for managing concurrency in multi-process React Redux apps, or said another way, how to get lots of things to do stuff good with React and Redux. So, all things considered, this actually describes pretty well what I am talking about. But since we're going to be focusing on concurrency as a core concept in this talk, we might want to do a little better. So, what is concurrency exactly? If you ask yourself this question, the first thing that might come to mind might be something like, well, it's that thing that my coworkers say is hard when we cause a lot of, I cause a lot of intermittent test failures. Yep. Okay, so it's when we do lots of stuff at the same time, We're doing stuff at the same time. But we're in JavaScript, so async stuff, I think. Wait a second, we're in JavaScript. JavaScript is single-threaded. How can it be concurrent? What's going on here? Well, maybe let's get a little help. So this is Rob Pike, and like me, he's apparently from Canada. Any Canadians here? Yes, woo, Canada, awesome. I like the US too though, love. Okay, and unlike me, so Canadian, that's cool, he's actually an absolute genius who's done a bunch of monumental things for software engineering, and one of those things is working on the creation of the Go language, about which he has a pretty famous talk. And that talk is called Concurrency is Not Parallelism, so that's a hint. And by the way, if you haven't seen this talk, go watch it. It's incredible. Please go watch it. So we kind of pose the question, if concurrency is not parallelism, what is it? And what he says is that concurrency is about dealing with a lot of things at once, which is a concept, and parallelism is about doing a lot of things at once, which is more of a physical property. So this is the more formal definition, which is that concurrency is the composition of independently executing processes. And it is that nature of being composed that is in being in communication, while also being independent, wherein lies the complexity we have to manage and also the power. Now, JavaScript is really interesting. It's a really interesting demonstration of how programs can be concurrent but not parallel, because JavaScript is single-threaded. It's literally impossible for two things to be executing at any given time. On the other hand, JavaScript programs can and often are concurrent. Through the use of callbacks, promises, generators, and lots of other things, we can create different conceptual threads of execution, even though they do not physically exist. So of course, when I said multi-process apps like Firefox or Electron-based stuff, I was in fact actually talking about physical processes. So these applications can actually be concurrent and parallel. But what I really want you to focus on is when we're reasoning about concurrency, we are reasoning about independent things that must communicate in some way. Okay, quick disclaimer before we continue, there's lots of ways of defining concurrency, there's lots of ways of thinking and dealing about these problems, so if nothing else, I at least hope you're interested in figuring out how to make sense of concurrency in your particular use case, okay? So get mad at me later, but that's my disclaimer. Okay, so let's look at some code and some examples. Because it helps to visualize this stuff with a real-world model, and also because I like to plug Firefox stuff, I'm going to use a project I've been working on in Firefox called ActivityStream. And it's basically just a feed of stuff you do in the browser, like your history and bookmarks and stuff like that. By the way, you can totally try this out if you're interested by installing it at testpilot.firefox.com. All right. So recall that in a multi-process application, we have 2 or more JavaScript runtimes that communicate in some way, right? So with ActivityStream, which is currently a browser extension, by the way, there's kind of 2 processes involved. There's a parent process, which has access to a bunch of privileged APIs, like your history database, as well as a content process, which has a DOM where all of the React can render. This is kind of an oversimplification, but that's okay. We also have a 2-way port that allows us to asynchronously pass messages between both processes, and for us, those messages happen to be strings. And this is a form of what is typically called inter-process communication, or IPC for short. And guess what? We have a lot of concurrency in ActivityStream. We've got to fetch data from various places in the browser, like your history database. We've got to, as the user browses, parse metadata from pages and cache it locally. We've got to respond to user interactions and animate, and also handle changes in browser state, like if your tabs are open, network stuff, all that good stuff. Okay. But before we talk about some of the better ways to handle this complexity, let's start with a model of concurrency that we're already familiar with. So we're going to start with a task, very simple. We're going to ask the Firefox parent process to get the most frequent sites from the history database, and then render those results in the content process in React. So this stuff, you know this, right? We're going to create a Redux store. We're connected to a reducer that's going to process our top sites. We're also going to have some kind of component that's going to render them. That's fine. So as you know, Redux gives us the ability to dispatch actions, which through reducers can synchronously update our state. But what if we need to do something asynchronous, like go fetch top sites? So how many of you have heard of Redux Thunk? Like everyone, right? Okay, good. So you know what it is. It's just a function that can then dispatch other actions at some point in the future, and it can do stuff with promises and whatever. So if we're talking to a server, for example, we might go and fetch top sites and pass it length 6. We're going to parse that response, and then we're going to send an action with our update top sites action creator or catch the error. Pretty simple. So this is a model of concurrency we're very familiar with. So it's not inconceivable that we might apply this model to message passing. So how do we do that? Well, we need to dispatch messages and listeners. So first we're going to create a promise where we start by dispatching a message. The implementation's not important here, so I've just used post message, whatever. And we give that message some weird name like tsping, at ActivityStream, whatever, and as well as some details relating to the query. And next we set up a listener for a response from the parent process called tspom. And finally we resolve the promise with event details. Of course, we also have to remember to remove that listener at the end of the cycle, or what's going to happen? Memory leak, yes, we're going to cause a memory leak. And if we're doing this in every single one of our actions, you can bet you're going to notice pretty soon. So for the parent process, we also have to add a listener for TS-ping here, which runs our query on the database, and then responds with a TS-pong message. Simple enough. And the good news is, well, this totally works. 2 message listeners, a thunk, and an action later, we have the data in our store, and we can render our top sites. Finally, this is actually how we wrote the first version of ActivityStream. So I can tell you from experience, you're going to have a bad time, okay? Like, it's going to be bad. Well, maybe you're better than us, so you're going to be fine, but we had a bad time. So why are you going to have a bad time? Well, you have to make sure, first of all, that in every action you're handling timeouts or errors appropriately. Notice that we forgot to do this in our little example, and if something went wrong, we would have just sort of got a silent failure. These thunk-style actions are obviously way harder to test with, because you're going to have to sort of stub out or fake that functionality for all of your listeners. And that's a pain for fetch, but it's even more of a pain if you've got like window.event listener. We also have a lot of data translation between our different processes. So we start with this message, which has a name and a details. We then send that up, and then it has to trigger a task, so a query. We then have to translate that back into a message, and then finally that message into an action, which seems kind of silly since we're actually in control of the whole system. And we also have to add and remove a lot of listeners, which can open up vectors for memory leaks a lot. So can we do better? Well, yes, I think so. So instead of thinking about treating our parent and child processes like a client and a server that require some layer of translation, what if we use actions to describe and communicate changes in all parts of the application? So when I say actions, I mean actions as plain objects. We usually think of these as describing synchronous behavior, but it turns out that combined with message passing, they can also be used to describe asynchronous or concurrent behavior just as well. So forget about that promise. We're going to express our request for top sites as a plain action that's, request top sites with some data with the length. Cool. And we're going to format those actions with something called a flux standard action. Who uses flux standard actions? Or some form? Okay, I can't really see very well, but not many, I think. So what that basically is just some constraints on which fields you have and what data they can contain. So we've got here a type. We've got a payload with the stuff that we're passing, and then we've got a meta and an error field. So the important thing is not that you use those exact fields, it's just that you have consistency in your entire system to help you both understand it better and reduce the need for data translation. So for example, we use data instead of payload because it feels more messagey or something, but that's fine. So how do we actually do the work of sending this request to the parent process? Well, what we're going to do is express this as a property of the action. In this case, I've added a meta field with a channel property, which says that this action needs to be sent from the content process where it originated to the Chrome or parent process. When we create some middleware, we create some middleware that will look at the meta property on the action and then dispatch the event if it sees that channel is equal to content to Chrome. So we've moved the message listener stuff out of each action into some middleware. Notice that in this case, instead of sending messages with unique names, we only have one message name, which is our channel, and the data associated is just an action. And this gives us two things. One, it means we only have to manage a single message listener per channel. And two, it allows us to use this model of actions as declarative expressions of change, not only inside of Redux, but also in the rest of our system, our multi-process system. So this is the parent process code now, which does not use Redux at all in this example, but suddenly it's starting to look a lot like a reducer or something. It's got a switch statement that when it receives the request top sites action, it will then respond with a response case. And again, we're now only creating a single listener per channel with one outgoing and one incoming event. Even better, we can have if we have some kind of shared module loader, which you may or may not have, we can actually import our action creators so that we're defining all actions in our system in the same place. And that's super cool. So the final step is that we're going to need to create some kind of store enhancer. on the content side, which will relay actions from our Chrome to content message channel into our Redux flow. And that's pretty much it. So this is a pretty simplistic model for doing a pretty simple thing, but I think right away we can see there are a lot of benefits. Because we've compartmentalized the work of message passing to a single place, we've now got much fewer listeners and less possibilities for bugs and memory leaks. And all of a sudden, all of our actions just became much easier to test, because when we're testing them or they're inside of React components, we just can create a spy and then look at the object that gets dispatched. If we decided we want to go ahead and put our React Redux front end on a different back end, like for example, we wanted to do activity stream for Chrome, or we wanted to make it just work on the web, we can do that a lot more easily because the implementation details of IPC are less tightly coupled from the expressions of what we want to do. And finally, because we're using a standard action format and a standard way of declaring how messages should be processed, we can compose those into higher order actions as well. So this is an example of a higher order action that we use called request expect, which adds a bunch of fields to the meta property, including an indication of which response action we expect back. So for top site's request, we want back a top site's response, as well as a customizable timeout. And all of this gets processed and kind of converted into our asynchronous actions by the middleware. And to use this higher order action, we just create an action creator, so request top sites, that then calls request expect with the two types of actions. We do have some limitations here, however. We've only got, in this case, we only have one channel in and one channel out. It's not like we have a bunch of processes going on. It's pretty much two directions. We're also only really dealing with a single kind of concurrency. As you probably noticed, there is also concurrency when we're requesting stuff from the database, but we're really only, in this example, dealing with the message passing part. And finally, actions, they are composable through the modification of the meta field, but they're not as composable as they could be for more complex situations. And to be honest, for many systems, including ours to a point, it's actually fine. But let's talk about applying these principles to some different problems, maybe more complex. So recall that I told you that activity stream is composed of two processes, a parent and a content process, connected by message passing. And while it's kind of true, it's also kind of a lie. It turns out that activity stream can actually be open at many tabs at once in one or more windows. So in terms of JS runtimes, what we actually have is a long-lived parent process that communicates with many different short-lived browser instances. And each one of those is going to have its own DOM, its own JS runtime, and therefore its own state. And this is also something that happens in multi-view Electron app, for example. So what we really want is for each one of those processes to have at least some amount of synchronized state. So some languages, like C, for example, implement IPC by having some notion of shared memory, which is memory that more than one process can access at a time. And you might know this actually has a lot of really tricky stuff associated with it, like mutexes and locks and whatnot. So it's actually kind of good that we have no means of doing this in multi-process JavaScript apps. But that's the case. We're going to have to use message passing. We can't use shared memory. One thing we might do to make things a little easier is actually move our Redux state into the parent process, which is thankfully pretty trivial since Redux is in no way tied to a DOM or a browser environment. And remember that in our parent process, the JavaScript runtime is a little bit different. We don't have a DOM, we don't have a window object, stuff like that. That's fine. So here we are. We're going to create a store in our parent process, ready to go. We might immediately start firing off some asynchronous actions to prime it with some data. Because we're also going to have to initiate changes from each tab, we're also, from user interactions and things like that, we're also going to have to start a store on the tab, and we're going to do that with some empty state. So what happens is, we start up the app, we prime some state in our parent process, and we open a new tab. Well, when we first load a tab, we're going to need to prime it with the current state of the application. So we'll have to send a message from the content to ask for the initial state and respond with a message containing the current state. So how do we actually replace the entire state of the store? This is actually not immediately obvious. So this is a pattern that is suggested by Dan Abramov and others. I kind of found an issue one day when I was like, yeah, how are we going to do this? This is weird. So, which, usually that's how you figure stuff out, right? In which you have a higher order reducer that will have a special case for an init action. So here we've got our init action is response initial state. And then you make your reducer as normal. But then you have this higher order reducer called make hydratable that's you're actually going to create your store with instead of just your regular reducer. And what this does is it receives that response init state action. When it receives that response init state action, it just replaces the first argument of your reducer, which is usually your previous state, with the state provided by the init action. Super cool, right? We could do certain things to make this more performant and not use message passing. So we could cache state in local storage that's shared, or we could even write directly to HTML if we have the ability to, when we're rendering, modify the HTML content of that page. But this totally works. The other thing, of course, is that we still need that enhancer that will dispatch events from the parent process. And we're going to need some middleware as well. So now for the case where all of your Redux stores will be 100% synchronized, and if the latency for message passing is negligible, the simplest way to do this would be to only call next on messages that are from the parent, and for all actions that we've dispatched locally, send them to the parent. So what we would do is kind of make a bit of a round trip, but it actually reduces a lot of complexity with sending messages to everywhere. So if you want, if you need more than that, you need to handle local actions instantly, or you want to be notified of only some parts of the state, not the entire state. You're going to have to think about filtering and identifying each source of each action. So one project I've seen that has some interesting ideas about this is Redux Electron Store, which you can check out on GitHub. Another interesting one I saw is this Redux Replicate project, which builds on the principles of state machine replication. And I wish I had more time to go into some examples, but go check them out if you're interested. So one more concept I want to introduce to you today is side effects. Now, actually, everything I've been talking to you about, like dispatching events, fetching data from various sources, all of that work can actually be considered side effects in that they are caused by changes in application state but operate in different conceptual threads of execution. So up to this point, we've handled side effects through a loose coupling of action properties and some functionality inside middleware, which improves things a lot. But you can imagine that we might have several different kinds of side effects, so different asynchronous flows that might even interact with each other in some way. So we're going to go back to our example of retrieving sites from our history, but now we're just going to kind of think about the part where we have a Redux store on our parent process and that needs to get some data, retrieve some history items. So when I first wrote this talk, what I was going to show you was an implementation of something called communicating sequential processes. And this is a model of concurrency that is adopted in many languages, including Go and Clojure. But it turns out that I'm already at 22 minutes in my talk, and also that there's this project called Redux Saga, which actually uses a lot of the same principles. So I figured it might be neat to talk about that instead, very briefly. So the core primitive of Redux Saga is called a saga, which is a lot like a Go routine if you've used Go. And the way it works is that instead of expressing the relationship between our side effects and our state as properties of actions, we instead spawn individual processes, not real ones, but conceptual ones, each dedicated to a particular thing. And they can be composed and also communicate with each other, just like the real processes in our app. So to give you an example of this, we want to handle the fetching of our history data. We're going to start by creating a saga called watch history request, which is a generator. And as I said, you can think of a saga as a process, not a real process, a conceptual one. And it kind of has something like its own mini event loop. So in this process, we can take events called request history that have been added to this event loop, and you can actually write this as an actual loop. But in this case, we have a little bit this function called take every, which is going to help us do that. So for every rec history event that we receive, it will direct us to this get history items function. And now that we have an action, we can call our function that does some querying. So that's a do history query with action.data, which is the query parameters. And finally, we can put a new action back into the system when we're done. You probably noticed this is all done with generators, which means we can write this in a kind of synchronous style, which is pretty cool, right? Another cool thing about sagas is that you can actually have lots of them running at the same time. In fact, you can actually fork new sagas or processes within sagas, just like you might do in Linux, for example. So we can handle metadata, we can go request history, we can do lots of stuff, we can do all kinds of multiple asynchronous processes in the context of a single JavaScript runtime. Very cool. So what's better about this? Well, we still have actions, and because of the nature of having many communicating subprocesses, we can have many different kinds of concurrent behavior in asynchronous flows. We have a much more sophisticated model of composition applied here, and again, I don't have time to go into the details, but please look up Redux Saga if you're interested. Another thing you might want to do, if this looks cool to you, is go look up a paper from the 70s called Communicating Sequential Processes by Stephen Hoare. So one more project very quickly I think you should have a look at, which is has a different approach, is Redux Loop. And it's sort of based on some concepts from Elm, which is this concept of effects. And the way that works is that instead of letting actions declare side effects, so in our meta thing, Redux Loop actually declares them in reducers. And I know it seems weird, but if you take a look at this, when you first glance at this, you're like, hang on a second, doesn't this make your reducers impure? And the answer is no, because what's being returned is just a declarative expression of what we need to do. Like with sagas, our message passing middleware approach, the actual work is handled in a separate thread of execution outside of the reducer. So definitely check that out, very cool. Okay, so I showed you a few things today. We've learned what concurrency is, we've learned some different problems about how we usually think about concurrency, and some possible ways to start thinking about dealing with them. But if there's one thing I want you to take away from this talk, it's this. The physical multi-process part of this talk was actually just a forcing function to give us some useful constraints and shamelessly plug cool Firefox stuff, but you can actually use these concepts anytime you do concurrent programming in JavaScript. So look at other languages that have different models of concurrency, get excited about it, and most importantly, go forth and figure out how to get your things to do stuff together good. Thanks very much.